Okay, so I'm going to share a Word document real quick that's kind of got most. So this is basically what the final consists of, like all the other tests. It just basically covers all the derivative rules and integrals that we've got. It doesn't use them all, but so I just kind of went through and picked the ones to really review. And then it talks about continuity and when a limit exists, when it doesn't exist, when a function is continuous, and stuff like that. Then setting up integrals of solids of revolutions, so like rotating stuff around axes. There's a problem like that. Then there's the first and second derivative test, what each of those mean. There's going to be a min-max problem, a related rates problem, a differentials problem, a definition of derivative problems, an improper integral, an initial value problem, and a work integral problem. So if there's something that you guys want to cover first, we'll start with that, but I was thinking you would just run from the top. You guys have something you want to cover first, or?
No, I think I want to go over some of the, what like the short answer stuff will be, but whatever you have first is great.
All right, so I will go back to my screen so people can see. And we will start with just derivative rules to cover. So I guess the first derivative rule, I guess, is the quotient rule. It's pretty simple, right? So if we have something like this, right, the quotient rule just says we take the derivative of the top, multiply it by the bottom, or if we label this f of x, g of x, it's f prime x g of x plus g prime x f of x. Right, so this one is really simple, right? Because it's pretty simple to find the derivative, so it's going to be 6 times 4x plus 1 plus 4 times 6x plus 7. And if we wanted to, we could multiply this out and put into 1, but I think this kind of covers it. So I guess the quotient rule is pretty simple, but there are questions with quotient rule problems in them, so I guess I would review it. You guys have any questions on this or no? All right. So I guess like there's product rules, trigonometric functions, exponential rules, chain rules, implicit stuff. So I like this problem because it covers a couple things, right? So this is a product rule. Oh, I messed up the quotient rule. I'm sorry. I did the product rule. I'm going to redo that first problem. I was thinking about the problem. So what was it, like 6x plus 7 over 4x plus 1? And so, all right, disregard that first one. So it's the derivative of the top, so I guess it was f of x times, and then it's going to be minus the derivative of the bottom times the top all over the bottom squared. So this is the quotient rule. Sorry, that was my mistake. I goofed up there. But essentially, we could go through and resolve this, right? So it would be the 6 times 4x plus 1. And it's going to be minus this 4 times 6x plus 7 all over our 4x plus 1 squared. All right. So this would be our derivative for this problem. All right. So are you guys good with this one now? All right. So that's the quotient rule. And then the product rule. I was thinking the product rule. I did the product rule for this one. So if we had something like y equals e dx sine x. Now this is the product rule. And we kind of split this up into 2 parts. We kind of label them like this, right? So we'll have the product rule is this now. right? And so the derivative of e to the x is simply e to the x, right? So it's going to be e to the x sine x plus the second part, which would be cosine x times e to the x. And that would be our answer. So I guess, so those are pretty simple, but this rule is important to remember, I guess. Don't miss it. Sometimes it's kind of easy to miss it when the problem is kind of condensed together. So the next thing is, I guess, more trigonometric and chain rule stuff. So we'll say y equals tangent of 6x squared. And so it's kind of like, so every time you have like this a trigonometric function, there's almost always a chain rule attached. But for example, if we had like sine of x, so the chain rule, the derivative of the inside, this one would just be 1, right? So it's really easy to forget that there's a chain rule, but there's always a chain rule attached onto every trigonometric function. So if we take the derivative of this, the derivative of tangent is secant squared, and then it's going to be times the original, or the times the inside function, or of the inside function. And then we're going to multiply it by the inside stuff, the derivative of the inside stuff, which would, in this case, is just 12x, right? And if we wrote out the rule, it would look something like tangent of u. If we took the derivative of this, that would equal secant squared u du. So, or I guess u prime is how they would write it. It's probably how you see the rule, but so just don't forget chain rules with your trigonometric functions. I don't think I'm going to cover all the trig rules because you can find pretty comprehensive lists of those online, especially like the inverse trig functions and stuff like that. Those are, you can find those, and so I don't think I should need to write those down. So next one we're going to cover implicit differentiation. We'll say 2x squared plus y squared. So the way you kind of think about these problems is you have to think about y as being a function of x. So somewhere out there's a discrete equation that describes what y is equal to, but because of that, we kind of always have to treat that there's a chain rule attached with each of these y's. So if we took the derivative of this first one, we got to remember that it's a product rule, right? So it's going to be the derivative of the first times the last, which would be y, so 1 times y, plus the derivative of the last, which we'll just write as dy over dx, or the derivative of y, right? Times x, right? And then we'll take the derivative of the other side, which would be 4x, plus 2y, and then we got to remember that y itself is a function of x, so we have to make sure that we remember this dy dx on the outside. And then we're going to simply put all our dy over dx terms on the same side and the other stuff on the other side. So we're going to have y minus 4x is equal to 2y dy dx minus dy dx times x. And if we think about it, it's parentheses, so draw some parentheses, and we can pull both of these out, right? So y minus 4x equals 2y minus x times dy dx. And to get our dy dx, we simply just divide across. And there's our answer. So implicit differentiation. Does this all make sense? Do either of you have some questions about this at all?
I just couldn't see how you got the left side at the beginning.
This
how
one?
you got how you got right under that. Yeah.
So this is a product rule. because we technically kind of have two different functions here. So we're going to have to do the product rule, which says the first derivative of the first times the second plus the derivative of the second times the first. And so if we say that this is our f of x, so the derivative of x is 1 times y, which is where our y comes from.
Oh, you just didn't write the 1. Okay, gotcha.
Yeah. Okay.
Cool. Thank you.
All right. Any other questions? Can you guys see this pretty well? Or
Yeah, we can see it pretty well.
all right. So, and once you get into implicit differentiation, there's some cool stuff that you can do with natural logs, which I think is what we're going to do next. So, let's say, for instance, we have a problem that looks like this. All right. Well, I don't know if we have a specific rule that describes a problem that looks like this, but we can use ln and the ln properties and implicit differentiation to solve this one. So we just take the ln on both sides, right?
Is the one on the exam going to be as easy as this one, or is it going to be a little more complicated?
I wouldn't say they're much more complicated than these, but I don't know. I've been doing this stuff for a little bit, so hey, in principle, it's the same thing where we're gonna take the ln's of both sides, and then we're gonna take this and we're gonna drop it out in front. So it might have a more complicated exponent, or it might have something like this down on the bottom. But so this is essentially just like the meat of what you would do. So then. So now we can rewrite this one as ln y, right? And then, so then we just take the derivative of this, which is 1 over y. So the derivative of ln of u, let's say, is going to be 1 over u prime. So it's kind of like the tangent functions, where a tangent function is almost always going to have it always does have a chain rule attached to it, but sometimes it comes out to be 1. So if we just did ln x, it would be 1, right? But in this case, we have y, so our derivative, our y, is going to be dy dx, right? And then we're going to take the derivative of this, which also is a product function, or a product rule, right? So we're going to take the derivative of the first, which would be 1, so ln x, times the derivative of the second, which would be 1 over x times x plus 4, right? And then to simplify it, we just multiply both sides by y to get rid of this on this side. So then we have all this multiplied by y. And then we already have y defined, right? So we're going to replace this y down here with our actual definition of what it is. So that would be our answer. Does anybody have questions about what we did for this? Or? All right. And for like the test itself, there really isn't much more covered than this. Like, I guess. So I don't know. Is there anything anybody else wants to cover with regards to derivative and derivative rules that they feel like they need help on? If not, we'll just move on to some integrals that I feel will be helpful for the test. All right. So I guess we'll just start with a simple U substitution problem. So this one is U substitution, or a good way to recognize U substitution is this difference in powers. And so we could just say that u is equal to x cubed plus 1 du. This is going to be 3x squared dx. And we can basically replace this dx with du. So we can rewrite our integral now as x squared u. And then our du over 3x squared. Because that's what dx is equal to, right? And then this x squared will cancel out. And we can pull this 1/3 out in front. The square root of u du, right? And then we'll rewrite this as u to the 1/2 power. And so then we just use general power rule. So we go up by a power, and then we divide by the new power. So it'd be u to the 3/2 divided by 3/2, or multiplied by 2/3. That's going to be multiplied by 1/3. And so I guess our problem would be 2 over 6. Or 2 over 9, my bad. We'll replace our u with our function. It's not going to be a square root. And then we'll remember our plus c at the end. And so this is a simple u substitution problem. I guess on the test, I would always just check first and always say to myself, is this a u substitution problem? And try it out. And if it is, then it's usually pretty simple. If it doesn't seem like you can solve it anyway, you might try something else as u, but there's some tricky stuff on the test. Yeah?
I was wondering how you can distinguish between whether you're using a U-sub or whether you're using integration by parts.
All right, so let's...
Like, is there a way to, like, look at it and be like, oh, this is going to be U-sub, or this is going to be...
So, an integration by parts usually has, like, an e to the x, or an ln x, or a sine, or a trig function with a Cartesian something. So if it's like x squared e to the x, that's usually given by integration by parts. Or if it's ln x squared, those would all be integration by parts.
Okay, cool. Thank
So it's usually if you got something with this, with something that's kind of abstract thinking way about. So
Sorry, could I ask you one more quick question?
yeah, sure.
Sorry, I don't mean to be the annoying person here. I am just wondering, when you are dealing with a definite integral with like an upper and a lower limit, why you don't have a plus c?
Because, so if you think about it, so, right, so if we have just, let's write the generic form. If we have an integral, right, so we'll write f, so we know that's f of b minus f of a, right? That's going to be our integral. Well, we can say that it's going to be the same function either way. So both of them are going to have a plus c tacked on, if that makes sense.
Yeah.
So I guess I'll write it like this.
But I don't need to write the plus c on the
No.
exam.
On indefinite integrals, you do, but if you're evaluating an integral, you don't.
You just write whatever the answer is.
Yeah, because if you think about it as this minus the second one, then you basically have plus a c minus a c, and they'll disappear, right? So when you're evaluating an integral, it just doesn't matter.
Okay, thank you. I'll shut up now and mute my...
No, that's fine. Questions are good. I think it helps everyone when you ask a question. So I think it's good. So we'll kind of go with a abstract substitution problem. It's not as straightforward as this one. So it will still be pretty simple, and you've definitely done these problems before, but just kind of a reminder. So on this one, it kind of starts looking like a substitution, but there isn't a difference of powers, right? So how do we do this one? Well, it's basically going to be a U substitution, but it's going to be a little bit weird. We're gonna actually say z is equal to x plus 1, right? But then we're just going to rearrange this one. We're going to say that x is equal to 1 minus z. And because if we think about it, if we take the derivative of this, we're just going to end up with dz equals dx, right? So when the time comes to replace this variable, it's just going to go straight across. It's not going to come up with any extra like 1/2 or something like that. So we can now rewrite our integral. We're going to say that it's going to be 1 minus z times z to the 1/2 power dz. And now we can multiply this z to the 1/2 in and solve our integral, whereas before we couldn't really solve it the way it was written, right? So we're going to have z to the 1/2 minus z to the 3/2. And that will be the integral that we have, right? So then that would be z to the 3/2, 2/3, minus, that would be 2/5 z to the 5/2, and plus c. And we can't forget, I guess, that we started with x variables, so we'll just go back in and we'll plug in our x variables, right? So 2 times x plus 1, 3/2 over 3 minus 2 times x plus 1 to the 5/2 over 5 plus c. All right, so that makes sense, kind of how we did this problem. So it's still a substitution problem when you have something that looks like this, but it's a little bit different than what we did for the last one. So either of you have questions on that? All right. So I guess next we will cover integration by parts, right? So kind of with your follow-up on your question, like how do you tell? Well, if I was to write this, you could kind of tell that it was integration by parts because of the difference. So we have a trigonometric with the Cartesian stuff. So to solve this one, we're gonna do the tabulature method. In this particular case, every time usually you see this in your equation, you're gonna want to say that's our u. And then our dv is going to be everything else. And that's because we can eventually get this to 0. We could never get this to 0, right? It would just keep going back from sine to cosine, back to sine, cosine kind of stuff. So then we'll just take our derivatives until we get to 0. And then we're going to write our sine of x, dx. And we're going to take the derivatives, or the integrals, sorry, of this until we get to the same number here. So the integral of sine is negative cosine x, and then negative sine to cosine to sine. All right, so that's I didn't space them out very well, but that's how many we need to go, right? And then we're going to draw lines like this. And it starts with positive, positive, negative, positive, negative, positive. And this is.
How do you know what the sign starts with?
What do you mean? This one?
Yeah.
How do you? Well, it's always going to start positive, and then it's going to alternate.
Is there a circumstance where it would start negative?
No.
Okay.
In this case, our first term is going to come out negative because of this, but
Right.
we're always going to start positive.
Okay,
So-
cool. Thank you.
Technically, it would start off negative if it was like negative x cubed, though, right?
Yeah, so if this was like a negative, it's kind of like what I was saying here. So we're always going to declare it positive, but it doesn't necessarily mean that the first term is going to be positive. You're right. So like how I said this is positive, right? Well, our first term is actually going to be negative because of our negative over here, right? So our first term is going to be negative x cubed cosine x, even though we started with a positive, right? And then our next term, we're going to have two negatives. So it's going to be plus 3x squared sine x. And then our next term is going to be positive plus 6x cosine x. And then it's going to be minus 6 cosine x. And this last one, which is kind of horizontal, the last one, it's always an integral. So if we wanted to write this out, it would be like plus the integral of 0 times the integral. But 0 times anything is going to be 0, right? So we can just say, well, this term we can just get rid of. And so that's why it's very handy to have something that goes all the way to 0 like this one does. Because then when we get to this last one, it just disappears, and we don't really have to worry about it. Does this make sense how we got this answer? Do you have any questions about this? I think we'll do one more integration by parts thing, but
Yeah, and the tablet method works most times, except if you get into like natural log, right?
yeah. So I'll actually do one with a natural log. So. So let's just say we have x to the third natural log of x, right? Well, I would be inclined to say, oh, look, we have x to the third. Let's declare that as u, right? Well, what's the integral of ln of x? You can't really go that way. So every time you see ln in an integration by parts question, you're always going to declare your ln of x as your u. And then our dv is going to be x to the third dx. And this one, we're only ever going to have to do twice. ln problem, so we're going to take the derivative of this and the integral of this, x to the fourth over 4 dx, right? That's it. That's as far as we have to go. And this comes back to the last one is always an integral. So if we set this up, we know the first term is going to be ln x times x to the 4 over 4. But then we're going to have this minus the integral of 1 over x times x to the 4 over 4. Right? And this x will just cancel out. And it would be x to the third over 4 dx. And now this is a solvable integral. This one's actually pretty easy, right? It's just x to the 4 over 16. And then we can add that into our term. ln x, x to the 4 over 4, minus x to the 4 over 16 plus c. So does that make sense what we did there? You have any questions about kind of how we finish that one off? Or are you guys good with that? All right. So, and I guess the only other thing I can think of with integration by parts to remember is sometimes we have something like this. No, let's make that a cosine x. Well, this one, both of them are just, so this one, if we take the integral derivative, it's always going to stay the same, e to the x, right? And cosine x is just going to flip-flop back and forth, right? So we need to figure out, so this is an integration by parts problem, but it's kind of strange how you do it. So let's say e to the x and cosine x, right? Well, that's just going to be e to the x forever, right? Well, this one, the integral is sine x and then cosine x, which is a negative. And this is how far we're going to take it on this one. we're going to do our integration by parts. So that's e to the x sine x. And then that's going to be plus e to the x cosine x minus the integral of e to the x cosine x, right? Well, we're going to do some algebra tricks. And we're going to just say, well, that's equal to, right? I'll rewrite that real quick. Well, now we can see that this term and this term are the same, right? So I guess we'll remember our dx's. So we'll just add this term over to this side, and we'll end up with 2 e to the x cosine x dx is equal to this stuff, right? And then we can divide it by 2 and divide this whole thing by 2. And this one is going to be our answer. That kind of makes sense what we did there? Yeah. All right. So I guess integration by parts can be tricky, but I feel like that's basically all the types of integration by parts problems that you will see. So, all right. All right, dang. We're not going very fast, are we? I guess, so the next thing is we're going to cover is like first and second derivative tests and graphing equations, right? So let's say we have y equals 4x to the third, x minus 2x squared plus 3, right? Well, let's say we wanted to graph this and we didn't have a convenient way of graphing this. So we're going to use the first and second derivative tests to figure this one out. So the first derivative test.
Are we actually going to have to like draw it out?
Yep.
Okay.
It's going to be a whole problem like this. So it's going to be, so if we take the derivative. All right. And so this is our first derivative. And when we set this equal to 0, these are critical points. And so if we saw it, we can pull an x out. So x equals 0, and when 12x minus 4 equals 0, which would be 1/3, right? So these are critical points. They are possibly mins and maxes, but that's kind of what the first and second derivative tests are for. So the way that I learned it is like let's make a number line real quick, and let's put our 0 and our 1/3 on our number line. And we're going to take the second derivative, and we're just going to plug in a point smaller than 0 in between 0 and 1/3 and greater than 1/3. So if we plug in like a -1 into our slope problem, this becomes a positive, and -1 squared is positive. So if you put a negative number, it's always going to be positive. So this, which means it's always the slope before 0 is increasing. Let's choose after, like a half. And if we're probably going to have to use a calculator.
And you plug that into the derivative, right? The first derivative?
Yeah. So we're plugging it into the first derivative because this is describing how our slope is changing.
Okay, cool.
So,
That should be a positive one.
this one. So 0.25 squared times 12 minus 1. So this one, if we plug in 0.25, this actually comes out to be a negative, like a negative 0.25 for this. And then if we plug in a 1 for this, it's going to be 12 minus 4, which is positive, right? So if we think about this, if the slope is increasing, and then decreasing, and then increasing again, we can say, well, this is going to be a max, and this is going to be a minimum, right? At these x values. So we know that the shape is going to look like this, and that matches what we know about the function already, because if we just look at a cubed function, and if it's positive, we know that it's going to be rising on the right and falling on the left. So we already know a basic concept of what the function should look like, but we kind of have to finish it off. So the question will always ask for inflection points, or at what point does the slope start changing? So we need to do a second derivative test. So we'll find the second derivative real quick, which would be 24x minus 4, right? So that's our second derivative. And we want to set that equal to 0, right? And this one's pretty simple, right? Because it's going to be 1/6, right? And these are called inflection points, points of inflection. And it basically determines whether it's concave up or concave down. And we're going to do the same process where we're going to come up with a number line. We're going to put 1/6 down. And we're going to say, well, let's plug in a number less than 1/6. So let's go 0. So if we plug in a 0, we get negative, right? Well, 1. We plug in a 1, we get positive. So, which is also going to match what we have, because this means it's concave down until 1/6, and it's concave up after 1/6. And so if we were to draw a graph now, we have some points that we have to take care of. So we know at x equals 0, and let's say we'll do it. So this is 1/6, and this is 1/3, right? And at this, so we know there's a max at 0 and a min at 1/3. But we need to find the actual, so these are just the x values. So we need to actually go find the y values for our graph. And so we have to plug them in to this equation, right? So if we plug in 0, it's pretty simple. We plug in 0, it comes out to be 3, right? And we know that the slope is increasing, and it's concave down all the way until 1/6. And then we know that 1/3 is a minimum, and I don't know if I really want to plug 1/3 into that equation. So we'll just say it's not going to be a very big number. It's going to look something like this, maybe. It's maybe shallow. But on the test, do this. Plug in 1/3 and find out your y value. But it's going to be small. And we know that our minimum is going to be here, and that our inflection point is at 1/6. I guess, is there anything people have questions about how to do this, or it's just kind of a tedious problem? It's kind of long.
There's only going to be one of these on the exam, right?
Yeah.
Okay.
Yeah, or you only have to do one of these.
Okay.
All right. So I guess the next one that I feel like we could cover is, let's do differential problems. So let's say we have like a Capitol building, right? It's got a dome on top. There's a flag coming off, right? And we want to paint this dome with paint. But we want to know how much paint it's going to take to paint it before we start, right? So we know that the volume, so we're going to say it's spherical, right? So we're going to say that the area of a sphere, or the volume of a sphere, is 4/3 pi r cubed. But we're only working with half of that, right?
Is the exam going to have the equation of volume on there, or
Yeah.
is that something we have to remember?
Nope. It's going to have it.
Okay.
So this is going to be the volume of our, I guess, our dome. Let's say the radius is 15 meters. So this would be 15 meters from one side. And that the paint, after it dries, so our dr is 2 millimeters thick paint. So some pretty heavy duty paint. And it wants to know what volume of paint we need, or like how much paint are we going to need to shell that up. And there's technically two ways to do this problem, right? We could solve the volume with 15 meters, right? And then we could solve the volume for 15.002 meters and subtract them from each other, and that would give us the volume of the shell, right? But they don't want us to do that because they want us to use calculus. So we'll do it with differentials. Let's simplify this fraction out and make this a 2 on top. So we're basically going to split our dv. So we're going to take the derivative real quick. So our 3's are going to disappear. And we're going to split this up. We're going to actually move this to the other side, multiply it. So we're going to have our change in volume is going to be 2 pi r squared dr. And now we can just, because essentially what we want to do is we want to find the change of volume, which will give us the amount of paint, or the volume of paint we need. And so we know that our change in radius is 2 millimeters, or 0.002 meters, right? And then our radius is 15 meters. So if we plug this in, 2 pi times 15 times 0.002. If we multiply that out, that will give us...
Is it 15 squared?
Oh, 15 squared. Oh, you got me.
No, you're good. I just wanted to make sure I'm like
Yeah.
doing okay. Okay, thanks.
And when we multiply this out, this will give us our volume, or change in volume between the two, and that's how much paint we're going to need. So
is this the shell method that we're doing?
so this is a differential problem.
Okay. Nothing like that.
So this, well, we'll get to those next. I have those put on. And so there's a differential problems on the test, and when I went to calculus, I didn't remember my teacher ever teaching it to us, and so I thought I might make sure that it was covered. But do you have any questions about what we did here or how we got this? All right.
The one on our test, is it going to be a spherical shape or a different one?
It's spherical.
Okay, thank you.
Yeah. But all right. So I guess next we'll. How much time do we got? Not a whole lot. I guess we'll cover the initial value problem. And so let's say we have a company that's marginal profit is described by this equation. And it wants to know how much it's going to cost. So if we say that the cost is 0 units, before they make anything, it's 0, right? The cost, so they haven't spent anything to make anything, right? And so what would be the cost after the first 30 units? or after the first 30 things they produce, right? So this one, initial value problems, every time you see this like prime something, you can always say, oh, that's going to be an initial value problem, and I'm going to be taking an integral. So we want our profit equation, right? So we're going to take the integral of this, and we're going to go 50x minus 1.3x squared over 2 plus c is equal to our profit, or how much we're going to make. So now what we need to do is we need to use our initial value to solve for this c. But it's pretty simple, right? Because when x is 0, so we're basically just going to plug in 0 for x and set it equal to 0. So we can say that c is equal to 0, right? So we can rewrite our equation. And now we're just going to evaluate this for the first 30 units. So instead of plugging in, so now we're going to say that p of 30. So we're going to plug in 30 for x. And I got this to be roughly like 915. So after the first 30 of whatever they sell, they make $915. So I guess you guys have questions about this? All right, I guess we'll just move on. But I don't want to take up your whole evening, and I definitely feel like I've covered some of this stuff before, so I don't think I'll do area between two lines. We won't cover that. And probably the definition of a derivative, unless you guys feel like we need to cover that. Do you feel like you guys want to cover those things? Or
One thing that would be nice is, I mean, if it's something that we should go back over, I struggle on trying to find out how to prove that e to the x, its derivative is e to the x on like 2 tests ago. And I don't know if we need to make sure that we know any proofs like that.
there aren't going to be any proofs on the final.
Okay.
So I don't think we'll have to worry about that one. But
And then what are some things that we should know that'll help us with, like, I think she mentioned there's like short answers or something like that.
so there's multiple choice answers, which makes it a little bit easier. And the rotations, which we'll get to here in a second, where we're rotating a shape around the x and y axis, those you don't have to solve. You just have to set up. So there are some things where it's just setting up integrals and you don't actually have to solve anything, which is nice. But
Can you go back over the setup of the 3 ways to find volume?
yeah, so the shell method, the washer method, and the disk method.
Yeah. And then like
Yes, please.
how it changes going around the x versus the y axis.
All right. Yep. So I'm going to use something really simple, but don't worry, because the one on the test is pretty simple. So it's actually about as hard as this one. So, but this will be nice to cover about how you set things up. So let's say we have the line. All right. And let's say it's bounded by the x and y axis. So it's a triangle. Not that complicated of a problem, but so let's say we want to rotate it around the x-axis and the y-axis, not at the same time, but separate times. And we'll walk through all the different ways that we could find the integrals for this. So there's the disk method, right? The washer and the shell. And the disk and washer method are the same thing, except for washer methods. There are two disk methods combined into one. So they're basically the same thing, just the washer is a little bit more complicated. And then the shell is a different way of thinking about the problem. So if we're going to wrap around the x-axis, let's use the disk method first. So we're going to go around the x-axis. So the disk method is pi times the radius squared times the change in height, right? So let's draw our shape. It's going to be a cone, right? It's going to look something like this. So our radius is going to be this, right? From here to the side. And our height is simply going to be dx. Does that make sense so far? And so, because we're just going to take kind of like these little cross sections per se, and we're going to rotate them around so we end up with a bunch of little teeny tiny disks. And so we can write this. So we know that the radius for this particular problem is just going to be our function, because if we draw a picture, we can see it pretty easily, right? So if we were to draw our function, our radius is going to be in the negative x plus 2 squared, and our height, or our change in height in this particular case, is going to be our dx. And now we need to set up our bounds of integration. And we're working with x values, so we're going to want our x. So we're going to go from 0 to 2. So in this particular case, it's pretty easy to see, right? I guess if we're going to do the same step with the washer method, we're going to have to change our problem a little bit. So let's say we wanted to rotate it around the line x or y equals -1. So let's say there's a gap now in here. So if we were to draw a picture again, it's still going to be a cone, right? Except for it's going to kind of have this hole in it. If that makes sense. It's going to be this cone with a hole that's running through the middle. Something like this. With this line y equals -1 in the middle. So now we have to account for this hole. So we're going to do, we want the radius, right? We want from here to here, right? So how do we get to that point, right? So if we're doing the disk method, we're still going to have our first integral, right? But now we're going to minus something, right? But in this case, since it's, so we're gonna minus an integral of, well, what is this distance right here? If we think of this as the origin, this is a -1 distance, right? And this will also be squared. And so this ends up being positive, right? So of 1 squared dx. So I'm sorry if it's hard to see, but this would be our setup for our disk method. So this is if we're doing disk method. Does this make sense how we set this up so far? Or are you still? Yeah. All right. And the only thing different about the disk and washer method is they take these two separate integrals and they put them together into one. So if we want, we could do that because our bounds are the same. So we could just say that it's going to be pi from 0 to 2 of the top radius squared minus the bottom radius squared. And that would be our shell method, or our washer method. So it's just taking these and putting them into the same thing.
What about if you're going across the
So-
y-axis?
So if we're doing the y-axis, I was about to get to that. So let's erase our picture because it's a little different. So the y-axis in this case, it's going to be pretty much the same thing, except for now we're going to want to, if we draw our shape, right? Let's draw our shape again. It's going to look something like this, actually, right? So now what's our radius? It's going to be right here, right? And our height is, our cross sections are going to be looking something like this. And we're going to rotate these like this around, like that. And so our equation to find our height, we're just going to have to flip this around. So instead of a y equals, we're going to have an x equals, right? So we're going to have x equals 2 minus y, right? And then it's the same thing. So if we're doing the washer disk method per se, then it's going to be our r squared dh, right? And pi is the same. Our radius is now going to be 2 minus y squared. And our dh, or our change in height, is going to be dy. And our bounds of integration would change too, but in this case, it's also 0 to 2. So that makes sense how we did that? So it's just flip-flopping our original equation. So that would be the disk method. And the washer method is the same thing. So if we said we're going to go around the line x equals -1, it's going to almost look identical other than this first part. But so are you guys, do you feel okay, a little bit better about the disk and washer method?
Yeah.
I feel good about it.
All right. So I guess we'll do the shell method. So the shell method is kind of a different way of conceptualizing the problem. I'll just redraw the whole thing.
Will we need to use all three of these methods on the exam?
So the solids of revolutions, there's one that is where you have to show your work, and then there are going to be two that are multiple choice that you could set up either way. Does it make sense? So you're going to have to know how to set them up every way so you can identify which one's right. Does that make sense? I don't know. So it would be useful to know them all, but if you wanted to, you could get by with just knowing the disk method. You could get by. But it might be easier to use the shell method in some cases. So technically,
I'm sorry, my kids were kind of being crazy when you answered the first part of that question. Did you say there was only one of these questions on the exam?
so there are two questions like this. There are multiple choice, and then there's going to be one that you have to solve completely. So I guess you don't have to know them all, but it would be helpful to know them all.
Okay, gotcha.
All right, so the washer method, so let's draw a shape. So let's say we're rotating around the x-axis again, right? So the washer method is saying, well, instead of making little discs, we're going to make like cylinders. So we're going to have kind of this cylinder shape in the middle, and it's almost like a donut if you envision this, so that the hole is empty, so there's nothing in the middle of it. And we're basically going to add up a bunch of those in a row around the x-axis. So if we're doing the shell method, we have our equation y equals a of x plus 2, right? We actually want to know this. If we generalize it, it's 2 pi times h dr. So it's just kind of a different way of thinking about the problem. So, and we're dealing with the change in radius. So the height, so if we think about the shape of the sideways, the height is going to be our function. But if we're rotating around the x-axis, it's a function with regards to x. So we're going to have to resolve this to our x equals 2 minus y, right? So we're going to have 2 pi times 2 minus y, and times our change in radius, which our radius is going to be r times the change, sorry. So it's going to be r dr, and our radius in this sense is y. So if we set this same problem up with the shell method, so it looks a lot cleaner. And once again, we're using y variables, so we're going to be on the y axis. So I feel like this is most of the case. Most of the case, we don't really have any squares, so we don't have to like FOIL a whole lot of stuff. So sometimes I think it is much easier to do the shell method than other ways. So I guess if we're rotating this around the x-axis using the shell method, we're going to have a shape that looks like this again, right? And instead, now we're going to want something that looks like this, right? That's rotating around. And so instead of, so if we get rid of these arrows, we're going to want our height, right? So it's the integral of our height, which this case is going to be our y value. It's going to be negative x plus 2. Oh, we can't forget our 2 pi out front. And then it's going to be our radius, which our radius in this case is just going to be x. And then we're going to times that by a little teeny tiny chunks in thickness, or dx. And this is also going from our 0 to 2. So the shell method, if you're rotating something about the y-axis, is usually a whole lot easier to use the shell method, because as you see here, we're rotating around the y-axis, and we got to keep it in our x variables. So if we rotate this one disk method, then we get to keep our x variables. So if you're clever, you would never have to rewrite your equation. You could just always keep it. So
hold on, can you say that again? You said if we are using the shell method and we're going across the y-axis, it will always be in x variables? Yeah,
so if we're rotating around the y-axis, usually it's pretty simple it's a lot easier to use this. Unless, of course, it gives us our equation as an x variable, then it might be easier to use the disk method. But the washer method is or the shell method, I think is my favorite. It looks a lot cleaner, and they're easy integrals to do. But I guess, are there any other questions you guys have about this? Or?
So if we're using the shell method and we're doing it across the x-axis, it'll always be in y variables.
Yeah, it's going to be the other way around.
Okay.
So it's kind of backwards in that manner from the disk and washer method, where if we're rotating around the x-axis in the disk and washer method, we're going to keep on our x variables. But if we're rotating around our y-axis, we're going to need to swap to our y variables. But So I don't know if I did a fantastic job at explaining this, but I know Khan Academy has some pretty stellar videos on the same subject. So if you feel like you need to understand it more or you don't understand it quite, I would definitely go find some help from YouTube somewhere, or maybe ask the teacher. But all right.
My only other thing that I'm concerned about is the fundamental calculus theorem. Like, what are some key things that we should know about that?
That's a good question. All right. Honestly, I can't really remember the fundamental theorem of calculus word by word. I know it's important in everything we do, but there's not going to be a question on the test to ask you to define the fundamental theorem of calculus.
Cool.
So, it's there and it's in everything you do, but it's fundamental to calculus. And if you really want to learn it more, I'm not the person to ask. I'm sorry,
All
but
right, sounds good. But as far as the
So
test
you
goes,
said we're not going to have to prove it then, right?
no, I don't think so.
Okay.
well, cool. I think I'm good then.
And I guess the last thing that I wanted to cover that you guys didn't really get to test on, I think it's a relatively new concept, is the work integrals. So finding the work of something. So if you've ever taken a physics class, you know that work is force times distance, right? It's how much force you need over the amount of distance you're moving something, right? Well, let's think about a building, right? And let's say we're hanging a rope off this building. Let's say it's like 120 feet tall or something. And this rope is like 80 feet. Who knows what we're doing, but we have it. And we'll say that this 80-foot rope weighs maybe 2 pounds per foot. So if we think about this, let's see. So let's ask, how much work does it take to lift the rope all the way to the top of the building? But if you think about it, it's a variable problem, because as we pull up rope, there's less rope to pull up, so it weighs less, and the force required to pull it up is less. So it's not very clear about this force times distance thing, because it's not a continuous force required to change it, right? So this ends up being a calculus problem, right? Because it's variable. And so let's kind of like zoom in on our rope, right? And if we take like a cross section of rope like this, we could say, well, that's a little change in height, or y. That's a little piece of dy, right? And let's say per se that little change in y is 1 foot. It's gonna weigh 2 pounds, right? Well, if this dy is 3 feet, it's gonna weigh 6 pounds, and so on and so forth. So if we wanted to write an equation, we could say that the weight, because the force of something is basically how much something weighs. And so we can say, well, our force is going to be 2 times whatever our dy is. And so that's our first part. And now we got to find, well, the distance we're pulling it. Well, if we're pulling it all the way to the top, well, let's think about it for a second. Let's keep it general. So we're going to pull a distance of y, right? Because if we think about it, we're going to pull y up. So we're going to have this y out in front. That's the distance we're moving, is y. And so that would be so if we rewrite this as 2y dy, because that looks better, that would be the force required to move a little section up, right? And this is where like the integral thing comes in, where, well, we can say we're going to take an integral and we're going to take all these little pieces and add them up into one, right? So we're gonna take our integral and our bounds of our integral, right? So we start at 0, right? But we're gonna pull 80 feet of rope, right? So we're going all the way to 80. And this would be equivalent to the work required to pull our rope all the way up, right? So if we take the integral, that's y squared, evaluated from 0 to 80, right? So our work would be 80 squared, whatever that is. And so if we wanted to take this one a little bit further, what do you think would happen? Do you think it's more or less work for the first half of the rope or the second half of the rope? So if we're going to pull up the first half of the rope, it would take more, right? Because then we just have this static piece of rope down. So it's kind of interesting. So at the beginning, it's going to take a lot of work to start at the beginning, right? And as we got near the end, it would take less effort. So if you like grafted or something like that, the amount of work, the work at the beginning would be really high, and it would peter off to nothing at the end, right? So yes, that's our work integral. I guess you guys have any questions about that?
Is Lucian, please don't. Is the work integral on the exam going to be in this form, or is it going to be like the olive oil in the cone thing, or?
It's not a rope problem, if that's what you're asking.
Yeah.
But,
how many work problems are there? Just one?
just one.
Okay. Okay, cool.
It's not a spring. I'll give you that one, because springs are a little bit different, but there's not one of those on the test, so I won't cover that.
So not a spring and not a rope. Gotcha. Thank you.
I guess so that's pretty much, I guess there's some other stuff that's on the test that we didn't cover, like area between two lines and definition of derivatives, but I think I've covered those in the past, and you guys have been doing those for a long time, so I don't think we'll cover that. But I guess, do you have any other questions or something that you feel bad about leading into this test that I can answer real quick, or?
Are you going to do another review with the other class?
No, so I figured that only 1 or 2 people show up from each class every time, and it's the same material covered, that this will be the one that I do, and that this would be for both classes. So this is the one.
Okay.
Cool. Thanks, Ben.
Did you happen to like 2 exams ago you wrote up like a list of everything that was on the test?
Oh, yeah, I think you missed it. I had that at the beginning.
Did you do that?
Yeah, I can share that really quick. I think it's already at the beginning, so I'll make sure I get this video up in the next hour, and you can go.
Okay. Yeah, you're good. Thanks so much.
All right. Well, I hope that this proves helpful. Good luck on your final. It's longer than all the other tests, but I wouldn't say it's necessarily harder. Like I said at the beginning, it's comprehensive, so they had to cover a lot of material, so they didn't really have time to put everything in. So
Okay.
there's some problems that you covered that aren't going to be there, but
Real quick, sorry, I just noticed. Can you remind me what a total accumulation problem is?
A total accumulation problem sounds like an integral, right?
Yeah.
I believe that's an integral.
Yeah, it's an integral problem, right? So
Yeah.
I think kind of what you're describing, I'm not sure about that one, actually.
She has it on her review for the final exam as one of the things that's going to be on there.
The total accumulation.
Yeah. Is that where like the sand is falling and like creating a pile or something like that, or is that something else?
I know there's like average value problems. So I think there might be one, but I don't think I prepared a problem for that. I'm sorry, guys. I wish I was more prepared for this, but
I'm sure I can
Hey,
just
Hiram.
Google or something.
Hiram, I'm meeting with the teacher tomorrow at 2, and I'll ask her about it. And maybe I'll find a way to email you or something.
Okay,
Yeah.
that'd be perfect.
I'm pretty sure that Khan Academy has it. It sounds just like an integral problem to me, like
Yeah.
a total
I
accumulation.
believe it's an integral problem because I know I had struggled with that one too, but I had to look it up and find out what it was because it's actually similar to something else, but I can't remember what it was.
I know that there's like average value problems where you find the integral and then you divide it by the total distance, but that's an average value problem. So, yeah.
Cool.
So I definitely looked that one up. I wish I knew more, but I don't think I've done one of those problems since this class like a year ago. So
If something does pop up and you think about it, and you can just send out an email with the video link. I mean, just
Yeah.
like even the setup of it, so I can like remember what they are, because I don't think it's hard. But
yeah, I definitely will do that.
cool. All right.
All right, no problem. I wish I could be more help, but
No, that's
I hope
perfect.
you guys